Morning, guys. Today we're going to take a look at page 12 of the Unit 8 Classwork packet. The topic for today is a square. Now, you could think of the square as a product of the marriage of a rectangle and a rhombus, because what happens is a rectangle and a rhombus, all of their characteristics are passed down to a square. All squares are also rectangles. All squares are also rhombi. Okay? Now, they list all the properties there for you. However, what I want to do first is in that blank space on the left, I actually want to make a diagram that shows exactly what we know about a square. In some ways, a square is actually the easiest figure to work with. Some people will disagree with me on that, but I stand by what I say. The reason in some ways it's the easiest to work with is you know the most information about it. All right, so let's draw this square and see what we know. Okay, so first things first. All squares are rhombi, right? So what that means is that every single side is going to be congruent, right? That's pretty darn helpful. Similarly, we also know that all squares are rectangles, which means that in the corners, I have 90-degree angles. But we can do even better than that. We know other properties of rhombi, right? For example, rhombi have perpendicular diagonals. What that means is in your picture, you should have all right angles right there. You also know that because all squares are rhombi, the diagonals are angle bisectors. Tell me this, guys. What happens when I bisect 90 degrees? What's half of 90? Oh. So what that means is I actually happen to know each one of these itty-bitty angles all around. Okay, I actually know that these are 45s all around, which fills in a lot of missing pieces. Last but not least, because all squares are also rectangles, I know that the diagonals are congruent to each other. And because all squares are parallelograms, I know that the diagonals also bisect each other. So what I can do then is this. Each piece of the diagonals is actually congruent. So I know this diagram is a little bit much to take in right now, but it's worth considering because of the wealth of information it gives you. For example, notice that virtually everywhere we look in this figure, we are dealing with isosceles right triangles. All right, isosceles right triangle. That's going to be important in Unit 9, so keep that idea in mind. All right. Notice also that we actually know the measure of every single angle in this diagram. And if we know one piece of a triangle, I can actually use the Pythagorean theorem quite easily to find the other pieces. Let's take a look at an example of how this might work, okay? And with that, let's take a look first at example number 6. All right, we're going to start off with example number 6. So many markers to choose from. All right, example 6. Okay, so example 6 is a pretty typical square. All right, in that I have two intersecting diagonals. The square's name, predictably, is A, B, C, D, and the intersection point right here is E. All right, now they only give me one piece of information about this square, okay? And that piece of information is that AD is 11. So what I'm going to do is I'm actually going to write that in my diagram, okay? Now, as a strategy, I'm actually going to take all the information I know, just because they tell me it's a square, and I'm going to plop it on the diagram, okay? So, I'm going to say, oh no, my poor marker. Looks like the green marker's dead, guys. Oh no. I know that you must be devastated. Okay, let's try that again. I know that all four sides are congruent. I know that in each corner, I have 90-degree angles. Further, I also know that because these are angle bisectors, each itty-bitty angle is 45. And because this is a rhombus, right, all squares are also rhombi, I know that these are all... What happened? My poor markers. Oh no. I have to throw these away. I know that these are all 90 degrees right here. Okay, 90, 90, 90. And I happen to know that each one of these pieces of the diagonals is congruent to each of the other pieces. So with that being said, we virtually have everything we need. There may only be one or two places in this problem where we need to solve. So let's go through. BC, well, if this is 11, that's also 11. AC, okay, I actually don't have that yet, but let's see how we can find it. Do you guys see, and I'm going to do this in pink, does everybody see a huge pink triangle right there? Notice that I have two sides of it. I've got 11 and I've got 11, right? I have two legs. So what I can do is I can use the Pythagorean theorem in order to be able to find the hypotenuse. Let's see how that works. 11 squared plus 11 squared equals c squared. 121 plus 121 equals c squared. 242 equals c squared. Rad 242 equals c. And if I were feeling particularly adventurous and I wanted to simplify, the biggest perfect square that goes in is 121, which is just 11. And so that would actually be, if I want an answer for AC, that would actually just be 11 rad 2. Now, BD, because the diagonals are going to be congruent to each other, BD would also be 11 rad 2. EC, well, notice that this diagonal is split into two parts, so EC would literally just be 11 rad 2 divided by 2. Kind of nice, right? All right, now everything else is pretty cool. Angle DAB, DAB, 90 degrees. Angle AEB, also 90 degrees. Angle CBD, 45 degrees. And angle BAC, also 45 degrees. All right, so again, a square is actually the easiest shape to deal with because you know the most information about it. The trick is make sure that you put the information you know in the diagram, and don't be surprised if you have to use the Pythagorean theorem every so often in order to find unknown side lengths.